Hi online learners, today we're going to be talking about how to predict chemical reactions and what different types of reactions there are. So we're going to go over synthesis reactions, decomposition, single replacement, double replacement, and combustion reactions all in this video. So it's going to be a pretty lengthy video with a lot of notes. Make sure you have your note sheet out in front of you that I provided via Canvas. If you don't have that, I would make sure you grab that out because it is a pretty step-by-step layout of the notes I'm going to go over now. So let's get started. So some steps for doing reactions in general. Our first step is always going to be to identify the type of reactions, which again we're going to learn about those types of reactions today. I did mention some brief overview of those reactions, but not exactly what they are. So we're going to identify the type of reaction. We're always going to predict the products based upon the type of reaction. We're going to use that as a model. So what we're going to learn today is that products are dependent on the type of reaction that's occurring. So you're going to be able to predict reactions or products of reactants based upon what type of reaction is occurring. That sounded really funky because I used the word reaction so many times. We're always going to be balancing something. You have already learned how to balance reactions, so you always are going to be doing that as well. And don't forget about those diatomic elements we learned about either when we were learning about word problems earlier in this unit. So those Brinkelhoff elements. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Remember, those will always be in pairs of 2. So like O2, for instance, is an element, or H2 or F2, because they can't stand alone. Okay, sorry, someone knocked on the door. So let's get started. The first type of reaction we're going to be learning about is a synthesis reaction. Hopefully you've heard the word synthesis before and you know what that word means. So a synthesis reaction occurs when two substances, usually elements, are combining to form a compound. So those sometimes they're called addition reactions as well, because it's taking 2 things or 3 things or 4 things and putting them together to make a less amount. So taking 2 and making 1, taking 3 and making 2 or 1. So we're synthesizing something, we're making something new. And that's a synthesis reaction. So again, it's a reactant and another reactant making one product. So an easy way to recognize this is if you have starting with 2 things, ending with 1 thing, so you immediately know it's a synthesis reaction. Then you have A and B coming together to make A and B. There should be a little mini arrow right here. So, for instance, we could have 2H2 plus O2 yielding 2H2O. So taking H2, reacting it with O2, bringing them together to make H2O, one product coming from 2 reactants. So synthesis reaction is the easiest type of reaction in my opinion, or one of the easiest ones. So here's another example, but let's do some practice problems with this. Oh, before that, another example, and this is just a real-life application of what something might look like. So here we have potassium, which is just a metal, as we know, combining with chlorine gas. And when those 2 things combine, they form here, they form KCl, so potassium chloride. So predict these products. So I want you to write and balance the following synthesis reactions. So sodium metal reacts with chlorine gas. Go ahead and take a moment and solve that reaction, and pause the video and resume once you have that done. Hopefully you've got the answer of Na, solid, plus Cl, gas, reacts to form 2 NaCl. Remember, when you're doing these and you're forming these products, you still need to identify would those form an ionic or covalent compound, and since it's a metal and a nonmetal, they are going to be forming a ionic compound, so you do need to take charges into account. However, in this situation, Na has that +1 charge, Cl has that -1 charge, so when they swap charges, we're just canceling them. We have the 2 on the Na and the 2 on the Na here so that we can balance those out. Ooh, I do see an error here though. Does anybody notice my error? This should technically be Cl2 here if my computer will unfreeze. There we go. Oh no, close your eyes, don't look. Okay, sorry about that. So it should be Cl2 because remember, Cl is one of those Brinkelhoff elements that I just told you about, and chlorine can never stand alone, so it must always be in pairs of 2. Let's try another one. Again, these should all be on your note packet outline, so you shouldn't have to write all of these down, just your answers. So solid magnesium reacts with fluorine gas. Go ahead and pause the video. Hopefully you got magnesium solid plus fluorine 2, again that's a Brinkelhoff element, reacts to form MgF2. And lastly, aluminum metal reacts with fluorine gas. Go ahead and pause. You should have this as your answer. Aluminum solid plus F2, so again that fluorine gas, is reacting to form 2AlF3. With these, make sure that you have this 3 here. That's a major mistake that a lot of people will make. Remember, aluminum has that charge of +3 because it's in column 13, and fluorine has a charge of -1. So when we swap those, we get AlF3 so that we can overall have a 0 balance on that compound. So next we're going to be talking about decomposition reactions. So decomposition reactions occur when a compound is breaking up into elements or simpler products. So decomposition is exactly what it means. Something is breaking down. It's the opposite of a synthesis reaction. We're taking one reactant and breaking it into two things. So A and B AB compound is becoming A and B separate entities. So again, it's the opposite of a synthesis. We're pulling things apart, we're breaking bonds, we're no longer forming those bonds. We're decomposing some sort of compound. So a real life example here is we can take mercury 2 oxide, so mercury oxide here, and we can pull that apart. We do have to apply heat to make that happen, so that's what that little delta triangle is meaning. But then we are left with just liquid mercury and oxygen. So, some exceptions here. Carbonates and chlorates are special case decomposition reactions that do not go to the elements. So remember, carbonates, so CO3, and chlorates, ClO4s, and stuff like that are a little bit different. So they're not going to decompose into carbon and oxygen. They're going to decompose into separate entities of carbon dioxide and a metal oxide. So we'd have the CO2. So for instance, we would have CaCO3, so calcium carbonate, is decomposing to form CO2 and CaO because calcium isn't going to ever be by itself here. Okay, the same with the chlorates. They're going to decompose to form oxygen gas and a metal chloride. So 2AlClO3 is going to form the AlCl3 and oxygen gas. So again, we're not forming aluminum and chlorate because we can't just have a carbonate by itself. It's going to always form CO2. We can't have a chlorate just by itself. It's always going to decompose into oxygen gas. So that's just something a little different that we have to make sure we're remembering. Carbonates and chlorates are fancy, okay? And that's something we'll revisit and get some practice with because that is just something tricky you'll have to remember. There's other special cases too, but for our class, these are the only ones we're going to be looking at. So let's do some practice with decomposition reactions. So go ahead and predict the products, write and balance the following decomposition reactions, just like we did with synthesis. So solid lead 4 oxide decomposes. So go ahead and pause the video. So you should have hopefully gotten PbO2 because that solid lead 4 oxide is going to simplify to PbO2 instead of Pb2O4, and we're yielding Pb, so solid lead, and oxygen gas. And remember, oxygen again can never be by itself, so it's always going to be an O2 element. Another one to practice here, aluminum nitride is decomposing. So first step again, write out aluminum nitride as your ionic compound and decompose that into aluminum and nitrogen. As usual, make sure you reach out if you have questions on this because we are covering a lot of material in this video. Let's do some more practice. So, identify each of the type of reaction of the following. Oh my gosh. Let me start over. Identify the type of reaction for each of the following as synthesis or decomposition reactions and then write your balanced equation. So, if we have N2 plus O2 yielding NO gas, is that synthesis or decomposition? Of course it's going to be synthesis. We're taking 2 and making 1. BaCO3 yielding BaO plus CO2. Of course that's going to be decomposition. We're taking 1 and breaking it into 2. Ni3 yielding N2 plus I2. Good. Again, that's going good if you got it. If you got it, bad. If you got it wrong, bad. But again, that's going to be decomposition, taking 1 and forming it into 2. Hopefully during that process you were also balancing them. Again, if you're having issues with balancing, make sure you reach out for extra practice problems. But for the most part, I think we're doing okay with that. Our next type of reaction we're going to talk about, we're halfway there, is a single replacement reaction. This is where things start to get a little bit tricky. So a single replacement reaction occurs when one element replaces another. So one thing is replacing another thing, and it's just happening one time. So for instance, as you can see down here, we have a guy plus a girl and a guy dancing, and then the guys are switching, so now this guy's by himself. So the girl is still being in the pair, the girl is never leaving, but just the guys are swapping, and that's what's going to happen in our reaction. So a metal is replacing a metal, or a non-metal is replacing a non-metal. So we're having an element in compound make a different element in compound. So for instance, we have A plus BC could create AC and B if A is a metal. Or if A is a non-metal, we would have A plus BC yields BA plus C. So it's very dependent on whether something's a metal or a non-metal, because remember, things can only combine if they're a metal and a non-metal in this situation to make an ionic bond. If we have something being added that's a non-metal, remember the non-metal again is always going to want to react with the metal. This will make more sense once we see it, because we also have to be looking at something called a reactivity series, which gets a little bit confusing. Another reminder, make sure your cation, so your positively charged ion, is always coming first, because that's how we name ionic compounds. Oh, another little reminder, H2O, when it's splitting, it is not H plus and O2, it's splitting it to H plus and a hydroxide. So, here's an example in a picture form. So we have lithium, so Li plus 2H2O, and what's happening here is this H2O is being split. Okay, and since that Li has a positive charge, the negative OH is going to combine with the Li to make LiOH, and then the H2 gas is going to be on its own. This can also happen with potassium and water. So potassium and water can react. Again, that water is going to separate into its OH and its H. Potassium, having that plus charge, is going to combine with the OH to make KOH, potassium hydroxide, and leave us with our hydrogen gas again. This is where things get confusing. I mentioned an activity series or reactivity series earlier. This will always be provided to you if you need to use it, but this is basically the list of reactivity in elements. So lithium is higher than rubidium, which is higher than potassium, which is higher than barium. So this is important to recognize. You will have to use these when solving single replacement reactions. Oh, give me one moment here. So let's do some examples. So 3Mg plus 2AlCl3. So predict, will these reactions occur? So we have magnesium, which has our positive 2 ion, aluminum, which has a positive 3, and chlorine with that minus 1. So if something is going to react, we're going to be reacting magnesium with chlorine. So can magnesium replace aluminum? That question has to be asked because magnesium is going to be taking the place of this aluminum to combine with the chlorine. Okay, the way we figure this out is we need to see, is magnesium more reactive than aluminum? Okay, the thing doing the replacing must be higher on our reactivity series, and magnesium is higher than aluminum, so magnesium can take its place because it's stronger. Because magnesium is strong enough, it has a higher reactivity to rip aluminum away from chlorine, so magnesium itself can combine with chlorine. So we'd get Mg plus 2ACl3, which we started with, is giving us aluminum and magnesium chloride. So now that you know that, have your activity series out in front of you and try out this problem. Can aluminum replace magnesium? Pause the video. Hopefully you recognize, oh, Ms. Verbrugge, that's an easy one. Of course it can't, because we just saw magnesium can replace aluminum, but of course aluminum can't replace it back because we just saw that aluminum is less reactive than magnesium. When this occurs, no reaction is going to take place. No products are going to be created because magnesium is stuck to that chlorine and it's not going to leave. Aluminum is not strong enough to tear that magnesium away so that it can bond with the chlorine, so you would simply write no reaction as your answer. Try out this one. Oh, sorry. This is a very similar problem, just worded a little bit differently. So we have magnesium chloride plus aluminum. So notice it's just written backwards. It's still not going to work. Just the order of the reaction doesn't determine how they react, okay? Magnesium and aluminum still want to switch places, but magnesium is still stronger, so aluminum is not going to be able to rip it away. Now we should have a new one. So, can iron replaced copper in this situation? Go ahead and pause the video, check out your activity series, form the products if they can form, and balance your equation, please. Hopefully you found the answer that yes, iron is able to replace copper because iron is higher on that activity series. Hopefully as your final answer, you got iron plus copper chloride is yielding iron chloride plus copper. And one more here, MgCl2 plus Br. So is bromine able to replace Cl? Because notice this time we are replacing the non-metal, not the metal, because we have magnesium and chlorine, so magnesium having our positive charge being our cation, chlorine having a negative charge being our anion, but bromine is also a negatively charged ion, so we're replacing our non-metal in this situation. Okay, there is no reaction here. So if we go back a couple screens, more than I thought, and look at, there it is, bromine and chlorine. We do have a halogen reactivity series as well, and chlorine is stronger than bromine, so bromine is not able to replace it. Let's go forward like 8,000 slides again. So try that out again. Another one. I want you to write and balance the following single replacement reaction equation. So try out this one. So we're given words this time and you have to make the whole formula. So zinc metal is reacting with aqueous hydrochloric acid. So first write both of your reactants, and I want you to go ahead and figure out, is this reaction going to occur, and if it can, go ahead and balance your reaction. Hopefully you saw that yes, this can occur. Zinc solid is reacting with 2HCl to make zinc chloride and hydrogen gas. And then one more here. Sodium chloride solid reacts with fluorine gas. Go ahead and pause it. Hopefully you came up with this. Actually, I might have lied. I might have one more problem for you to try out. Aluminum metal reacts with aqueous copper 2 nitrate. This problem can again be solved. Hopefully you got this as your answer. If as you're working through these you're noticing that you're not getting these right, please reach out as soon as possible so we can figure out what you're doing wrong and we can get this under control before we get too far into the unit. So, almost done now. Double replacement reactions. So a double replacement reaction is exactly what you assume it will be. It's when a metal replaces a metal in a compound and a non-metal replaces a non-metal. So we're not just moving one thing this time, we're moving two separate things. We're having two compounds, ripping them apart and changing both of them. So for instance, we might have A and B plus C and D gives us A and D and C and B. These are easy ones. We're just moving each non-metal, we're removing the metals and replacing them with one another. So, for instance, you're going to think about it like foiling in algebra. So the first and last ions go together and the insides go together. So as you can see here, we have AgNO3, so silver nitrate, and sodium chloride. We have Ag, which is our positive, and Na is our positive, NO3 is our negative, and chlorine's our negative. So if we have this positive Ag here, it's going to combine with our negative chlorine. This positive sodium here is going to go with our negative nitrate. The major thing to make sure you're paying attention to when you're doing this is you're not going to write NO3Na. Because remember that cation, that positive ion, always gets listed first. When you're doing these as well, oh, school's done, sorry. When you're doing these as well, make sure you're paying attention to charges. Because as you can see down here, barium had that positive 2 charge, so that 2 went here. But here we don't need it to because barium and sulfate are able to balance each other out since they both have a charge of 2. When we're doing these, however, we do need to pay attention to something that also gets a little tricky. So with single replacement reactions, you're looking at reactivity series, and with double replacement reactions, you need to pay attention to the solubility rules. I will also provide you with these rules. So most nitrates are soluble, meaning they'll be aqueous. Salts containing group 1 ions and ammonium ions are soluble, whereas other things aren't soluble. And soluble basically means that they can dissolve in water. So You will also be given a solubility table, and you'll have to be able to know how to use this. So this is basically how you determine if something's aqueous, solid, liquid, or gas when they combine. So let's say we're combining a calcium and a chlorate. When those combine, it's going to make something aqueous. Notice if there's nothing here, they generally aren't going to be combining. They can also form solids though. So here's an example. We have potassium carbonate and a barium chloride combining to form a potassium chloride, and that's aqueous. So let's go back to that table. So if we find potassium and we find chloride, so right here, we can see that it's forming an aqueous compound. So that's how you know whether something's aqueous or solid. And again, I will always provide you with this type of table when you're solving these. You do not need to remember this. So let's do some practice here. So you're going to be predicting the reaction that occurs when you combine aqueous solutions of iron 2 chloride with aqueous sodium carbonate. Again, if the reaction occurs, write a balanced chemical equation showing it, and make sure you're showing your phase notation. So if you need, make sure you pull out that solubility thing. And I actually don't recall. Let me look if I gave you one of those in your notes, because I don't remember. But go ahead and try that out. I did give it to the in-person kids. I'll be sure to link this in the important documents so that you guys have access to it. So pull it up there. So go ahead and pause the video if you haven't already. Hopefully you figured this out. So we have iron 2 chloride, which iron has that +2 oxidation number, and chlorine with the -1 oxidation number. We're going to swap those charges just like we always do to make it FeCl2. And you're going to do the same for those other 3 compounds. Hopefully you're feeling comfortable at this point switching those charges and forming those ionic compounds that we learned last unit. Once you do that, you can go ahead and balance everything. Once you balance, that's when you're going to visit your solubility table. So you need to figure out if something is soluble or insoluble. So is it aqueous? Is it going to be able to be dissolved in water, or is it going to be a solid? So we hopefully learned that NaCl is aqueous, and FeCO3, iron carbonate, was a solid. So there is some practice in your note packet. Go ahead and try those out at this time. Go ahead and pause the video and try all of those practice problems. And here's the answers to those. So go through and check those answers. If you have questions on these or got any of these wrong and can't figure out why, please email me right away. Our last thing we're going to go over, and then we're done. I'm sorry this video is so long. I also haven't enjoyed making it that much. But we're getting all the notes done now so we don't have to take more notes later. Combustion reaction. You've heard the word combustion. You know what combustion means. Combustion reactions occur when a hydrocarbon is reacting with oxygen gas. A hydrocarbon is just a carbon that's attached to a hydrogen in some way. So this is burning. It's literally just combustion. It's burning of things using an alcohol usually. Okay, in order to burn something, we need 3 things in the fire triangle, which you've also learned at some point, I'm assuming. We've definitely talked about it in class when we're doing labs. But you know that in order for a fire to burn, you need a fuel, so a hydrocarbon, so some sort of fuel. Generally, it's an alcohol of some sort. You need oxygen, so if you cut off the oxygen, the fire will not burn. And you need some sort of ignition, so some sort of spark of some sort. With combustion reactions I think are also pretty easy reactions to identify, because every single time our products are going to be CO2 and H2O. Every time, no matter what you're putting in, CO2 and H2O are always coming out. So incomplete burning can cause some byproducts like carbon monoxide, but we're generally not going to be talking about those. You know what combustion is again. It's burning. It's used to heat your homes. It's used to run your car. Most of your life is run by combustion unless you're using solar green energy. Combustion is how we as an American society are functioning. So generally you're going to be using octane, so it's in gasoline, so C8H18. That's an example of one of these hydrocarbons. So an example would be C5H12 plus H8O2 is yielding 5CO2 and H2O. So again, you see that CO2 and H2O are our products. So go ahead and write the products and balance the following combustion reaction of C10H22 and O2. Hopefully you immediately recognize that CO2 and H2O are our products, and all you have to do is balance from there. And I didn't balance it there. let's see, what would this be balanced as? This should be a 10, and I believe that should be an 11. I can't do this in my head. One moment. Okay, sorry about that. So you should have 2 C10H22 plus 21 O2, yielding 20 CO2 plus 22 H2O. Here's some mixed review to do. These are in your packet, so go ahead and try out these. Pause the video. Hopefully, again, you received these as your answers. So this first one is a double replacement. The second one is a combustion reaction. The third is a single replacement. The fourth is a synthesis, and the fifth is a decomposition. I believe that is all the notes we're going to go over today. So that was a lot. You do have some homework to practice these with, but please reach out if you have questions. Revisit parts of the video, as there's so many practice problems in this video to help you better understand things. Let me know if you have questions. Have a lovely day.